Hello my happy tree friends and spats. So today I'm doing a little bit of a different kind of video. That is because earlier this school year I've sat on a problem. I've had a lot of fun with it. However, on the internet I could not find anything on it. So hopefully if anyone else has the same problem and doesn't want to do it themselves, this hopefully makes it a bit easier, I guess. But by the way, if you're looking at it and don't know whether you should just watch a video or do it yourself, I gotta recommend doing it yourself because it was a lot of fun doing that. It took a while. It took like 2 weeks if you discount the breaks I took in between or something like that. I don't remember. But it was definitely worth it. It's definitely a good experience to have. So yeah, I'm just gonna write down the term first. So basically what we are looking for is a generalized chain rule. So probably know the chain rule of a regular derivative, but we're gonna generalize it for the nth derivative. And what that's gonna be is the same function f times the product from k equals 1 to n. The n is not that important, but it has to be at least n, it can be bigger. You'll see in a second, of sum of ak equals starting at 0 to ak minus 1 of the same ak minus 1 over ak. That's a binomial. You should hopefully know those if you're looking at this. And times g to the ak minus 1 minus ak's derivative times f to the kth derivative divided by f to the k minus 1th derivative. And there's some conditions to this. First one is a0 is going to be equal to n. That one's important. That basically just says where you start with the product. And sums from ak equals 0 to ak minus 1 of whatever are going to be 1 for every ak minus 1 not element of the natural numbers without 0. That basically just says that whenever you have a sum from 0 to -1, or like from 0 to something undefined, you just cross that out and multiply with 1 instead. So yeah, for the proof, what I'm also going to use is the product rule. There's a bunch of proofs of that on the internet, so I don't think I'll need to prove that one. But basically, f times g to the nth derivative is going to be a sum from k equals 0, or I'm going to use a equals 0 later, so I'm just use a instead, to n of an n over a times f to the 8th derivative times g to the n minus 8th derivative. The order of those is not relevant. It's going to be the same thing when you do g to the 8th derivative and f to the n minus 8th derivative, but I think that was the way I did it here. Yeah, I think. All right. So for the proof, we're going to do this by induction. So basically for n equals 1, it's a little bit of a different kind of induction though, so I'll explain that in a second. So for n equals 1, we're going to have this term with a product from k equals 1 to 1 from a sum from a. I'm already going to write down k as 1 because k is only ever going to be 1 to 0, and over a0 minus 1, which is going to be 1 minus 1. 1 minus 1 over 0 times g to the 1 minus 0th derivative times f to the first derivative divided by f to the 0th derivative. And as we can see, the product is irrelevant since we only have one term. So we have f times the product from 1 to 1, so we can cross that out. The times the sum from 0 to 0, that's also just one term, so we can cross that out. At 0 over 0, that's a binomial. You should know that that is 1. And g to the first derivative minus the 0th derivative is going to be g to the first derivative times f to the first derivative divided by f. We can cross these out. That makes nothing, and that is f prime times g prime, which is the chain rule as we know it, so that works out. So for the induction hypothesis, instead of just saying that this works for one arbitrary n, we're gonna need this to work for every arbitrary for every n up to an arbitrary n0 or whatever you want to say that. but we're gonna have to start at n equals 1 anyways. So basically, for the case of n equals 4, we're not gonna just need the n equals 3 case, we're gonna need the n equals 1, the n equals 2, and the n equals 3 case, but those are anyways included in the induction. So it's a bit different than a usual induction, but it works under the same conditions. So yeah, and now for n plus 1, and now we're gonna use the induction hypothesis that this already works for this up to this one whatever n. So we're gonna figure out the f of g n plus 1. That's, hang on, there's the bracket matrix. All right. And what this is gonna be is basically, hang on, I'm just gonna rewrite this. The first derivative, then taking the nth derivative of that. And we know how to take a chain rule, and that is gonna be basically f prime times g prime to the nth derivative. And now we can't quite use that rule quite yet because we have a product, but we can use the product rule, and that's what we're gonna do here. I'm just gonna write it below. It's gonna be a sum from a equals 0 to n of n over a of I'm gonna write the g1 first, n minus a times g prime f n minus a. Don't forget we have the prime here. Almost forgot that. And f to the 8th derivative. But a, as we can see here, that is gonna be going from 0 to n. And we the induction hypothesis, as I've just said, we just need the derivatives up to n, and we have those. So we can use a chain rule for this here now with our hypothesis. So that's gonna be sum from a equals 0 to n of n over a of g. Since those are all derivatives of x, I'm gonna be writing this as n plus 1 minus a. Because, yeah, as I've said, they're all the same derivatives, so we can just add them. And then we're gonna use the chain rule here, but for f prime instead of f. So that's gonna be f prime times a product from k equals 1 to n of our sum from ak equals 0 to ak minus 1 of ak minus 1 over ak times g to the ak minus 1 minus ak derivative times this f prime to the k, f prime to the k minus 1. But since those are all also derivatives, but against those are all derivatives of g, we can just write this as f to the k plus 1th derivative divided by f to the kth derivative. And what I'm also going to do is multiply an f to the front and divide this by an f. We basically just multiply with 1. Assuming that f is not equal to 0, and if f is equal to 0, then we're never going to need this rule anyways. We can just do that, all right? So for our next step, we're basically gonna, hang on, let me just check. Okay, yes, so basically I kind of forgot that this, yeah, I kind of forgot to write on the a0 equals n part here. So I'm gonna write it at the very top of this thing just because I think that's better than to have this obnoxious thing to the side of it. So a0 in this case is gonna be, not n, it's gonna be a actually. I accidentally wrote n instead of a. However, that's also fine because as we can see, every term from a on is gonna just be 1, and n is always gonna be bigger or equal to a. So we're basically just multiplying with 1 a bunch of times. That would have been the next step, which is why I just got confused. So yeah. So that, however, that's just gonna be, hang on, we might be just done here. Yeah, we're basically done here. And we're just gonna change the index real quick. From I'm just gonna write this. I'm gonna leave it as this for now. I'm gonna do that in one more step, just to have it a bit more clear. Times product from k equals 2 this time to n plus 1. And then we're going to have to fix everything like this so it stays the same. Ak equals 0 to ak minus 1. We can leave that the same because those are just indexes. But what we can't leave the same is that a1 is a0 is going to have to be a1 this time because yeah, for k equals 2, we're going to have ak minus 1 being a1. So this time that is going to be a. We're going to have the same term here though. Times g. Since those here, everywhere the k is just the index, that doesn't actually change any of the values. Where it's going to change something is here, because this time instead of having k f to the kth plus 1 derivative, we're going to have just f to the kth derivative. That way for k equals 2, for k equals 1, we would have the second derivative, and here for k equals 2, we also have the second derivative. Same thing for k equals n and k equals n plus 1. And we're going to do the same thing here at the bottom. That way we have the k minus 1th derivative. And we're basically done here. Just have to now call this bottom a, not a, but a1 this time. Because our a1 is equal to this a anyways, we could just call that the a1. And that way we also don't have to write that down again for now. Oops. Hang on. That has to be an n plus 1 minus a. F prime divided by f. And this exact same term here. It's a bit obnoxious to have to write down the entire term on every step, but I guess that's just how maths is. The one thing we can leave out is, as I've said, the a1 equals to a, because I just wrote that down here, basically. And so, yeah, that, however, is also n plus 1 minus 1. And yes, we can, and now we can just say, we can just define ourselves another a0, and I'm going to define that to be n plus 1. That's actually not the way I did it on my proof, but I think this should make it a bit more clear with what I'm doing. a1 equals 0 to a0 minus 1. And then that is gonna be, we can just add plus 1 minus 1 here as well. So we have a0 minus 1 here as well over a. Then g, we see n plus 1, we're just gonna call that the a0 minus a. And f prime divided by f, and the same product, k equals 2, n plus 1, sum from ak minus 1 over ak equals 0. I might be forgetting some terms on some steps, but yeah, you'll notice when one part of the term is missing, but I don't see anything missing right now, so that's fine. And yeah, as we can see, if we had the k equals 1 term, we would have sum from a1 equals 0 to a0 minus 1. And yeah, we would have a0 minus 1 over a1. I forgot to write the 1 here. And I've also forgot the 1 here. And I also forgot the 1s up here, damn it. Alright. And then we also have the g to the a0 minus a1's derivative times k to the first derivative divided by f to the first derivative divided by f to the 0th derivative. And that's literally the exact same thing we have here. Hence we have hence we can add this to the product. And that's just going to be the k equals 1 term to this time n plus 2. And it doesn't really matter. Hang on. Oh yeah, I forgot. This n plus 1 has to be the a0. No, wait. I'm doing bullshit. This was right. Jesus Christ, hang on. Let me just recheck. I'm being extremely stupid right now. I'm adding the k equals 1 term, not the k equals n plus 2 term. So I was just confusing myself. And that's what happens when you just change a proof mid-video. It's still a valid proof though. And I just wrote the term wrongly again. So product from k equals 1, because that's the term we're adding, not the n plus 2 term. Jeez. To n plus 1 of a sum from ak equals 0 to ak minus 1 minus 1 of ak minus 1 minus 1 over ak. And this exact same thing here. And if, as we have said here, a0 will just be n plus 1. And this first condition we started with, this one, that always stayed the same. So yeah, that's basically a proof, because that's just what we wanted to show. This is the exact same term, but instead of n, we have n plus 1, and instead of starting at n, we are starting at n plus 1, and we were trying to find it for n plus 1. So yeah, that's quite a beautiful proof if you had to ask me. It's just a bunch of huge terms, but they cancel out. Not they cancel out, but like they work out really nicely. So yeah, hopefully this helps. And that's gonna be it for today.